Okay, the last section we are going to take a look at for this week is 11.1, and this is on what we call sequences. Okay, chapter 11, our last chapter, is on both sequences and what we call a series. A sequence is basically just a list of numbers. A series is when you add up that list of numbers. Depending on how big the list is, it's not practical to add thousands and thousands of numbers by hand. So what we're going to be working towards eventually are formulas to either figure out maybe what the 500th term in a sequence would be without having to write them all down, or adding up 500 terms in a sequence without adding them all up by hand. Those are basically what we're going to look at. So a sequence of numbers is just a set of numbers that has a specific order. So this particular sequence I just wrote down is sequence B. And when we want to refer to the terms in the sequence, we use usually a lowercase letter and a subscript. So if you put down B sub 1, that means that is the first term in sequence B. B sub 7 would be the 7th term in sequence B. B sub n, in general, just stands for the nth term. Now, this particular sequence is what we call finite. Finite means that it stops somewhere. If you see dot, dot, dot as the last thing in a sequence, then that means it keeps going. So I don't know where this one stops, but it does stop somewhere. Maybe it stops at 1 million terms, 20 million, 50 million. Maybe there's only one more term after this one. We don't know, but it stops somewhere. Any sequence that stops somewhere can be added up. Even if there's 50 million numbers in it, you can add them all up. That's not impossible, especially for computers or something like that. An infinite sequence, if we want to try to add all those up, we're going to talk about that more in 11.2. It depends. Sometimes you can add up infinitely many things, sometimes you can't. But again, that's something for the next section. For a sequence to be uniquely determined, there has to be a rule to calculate the terms. There has to be some type of rule to calculate the nth term. We're going to talk about two different types of rules. One type allows you to directly find any term you want. So if you want to know the 3,407th term, you can plug in the number 3,407 into a formula, and it'll give it to you. The other type of formula we're going to look at requires you to figure out every single term before the one you want to know. It's usually easier to come up with a formula that way, but it's not as useful. Because that means if you want to know the 207th term, you have to know the one before it, 206th, and the one before that, all the way to the beginning. So that type of sequence formula, not as handy, but it's usually easier to figure out. So we'll talk about both. All right, let's look at this one and just see if we can figure out a formula for this sequence without me really even explaining anything. First of all, it is infinite. It does go on forever. And does anybody see, or even in words, you don't even have to write a formula, but can you describe to me in words how to get the terms in the sequence? Yep.
Add 3.
Can you be more specific?
Add 3 to the previous number.
Okay, so that is one type of formula. Take the previous one and add 3 to it. So if you wanted to get the third term, what's the term before a sub 3?
Sub 2.
A sub 2. But to get the third term, it requires you to know the second one. There's a formula here that needs the second one. So now you got to figure out the second one. How would you get the second one? Sorry. What is it?
The first one.
The first one?
Plus 3.
Plus 3. Now, the first one has to be given to you. Now you can work your way back up. Okay, I've got the first one. Plug the first one in here. 2 plus 3 gives me 5 for the second one. Now plug the second one in here. 5 plus 3 gives me 8 for the third one. And you can work your way through it that way. So in general, this is the term before that. This is the term before that. What's the term before that? Yeah?
A n minus 1.
A sub n minus 1. So this is a correct version of the formula. That's called a recursive formula. Easier to come up with, not as useful, because if I want to know the 978th term, you're going to be adding 977 times from the first one to get to that one. No good. So can anybody figure out another version of the formula? But this time I want to base it on the position it is in the sequence. So this is the first one, the second one, the third one, and the fourth number. I want to see something I can do to this number to get this number. Yep?
N minus 1 times 3 plus 2.
So you're saying take this number, let's try it. Take this number and do what with it?
Minus 1.
Okay, that gives me 2.
And then times 3, and then plus 2.
And then times 3, and then plus 2. All right, that might, can you say that again? Take this number and do what?
Minus 1.
Minus 1.
And then times 3.
Times it by 3, okay.
Plus 2.
And then plus 2. Let's simplify what you just said. All right, so 3n minus 3 plus 2. So 3n minus 1. So the idea here, if his idea works, is take the position, triple it, and minus 1. If you triple this, you get 6, and minus 1, you get 5. If you triple that, you get 9, minus 1 is 8. If you triple 4, you get 12, minus 1 is 11. So that formula does work. Yeah. And there's a name for the way you wrote it versus the way I wrote it. I'm going to use the simplified version. But the advantage of this one versus the one on the left is if you want to know, I don't know, the 500th term, all I have to do is 3 times 500 minus 1. It's 1,499. Done. Any question on the difference between these two? And I'll tell you what each one of them is called in a minute. Okay, so first of all, a function, if you think of sequences as functions, you can write them as a formula. The only restriction is you're only allowed to plug in integers for the domain. Take the formula we just had. That's something you could graph if it was y equals mx plus b. It's a line with a slope of 3 and a y-intercept of -1. Now, if you were graphing it, it would make sense to graph it and connect it with a line. Because you could plug in any number if it was y equals mx plus b. But when you're thinking of it as a sequence, it doesn't make sense to plug in any number here. This n represents a position. Positions can only be positive, and they can only be integers. There's a number in the first position, there's a number in the second position in the sequence. There is no such thing as like a 1.5 position. All right? So when you're writing down a formula for a sequence, remember that the domain for this number, this letter, is integers. Okay? Specifically positive integers. It doesn't make sense to try to find the number in the 3.7 position. You want the one in the third or the fourth? There's nothing in between. Any questions on that idea? So essentially, if you graph this, it doesn't look like a line, it looks like dots, where you have a dot in each integer. You don't connect the dots. Okay? If you connect them, then you're using all real numbers for the domain. So I mentioned there's really a couple different types of sequences. The first one has to do with the length of it. An infinite sequence goes on forever, and that means you can plug in any number into its formula that is a positive integer. You can plug in 10 million. You can plug in 20 billion. You can plug in any position you want because it goes on forever. Compared to a finite sequence, it stops. Okay? It does not go on forever. So let's say I wrote this down, and I said, here's my sequence of numbers. So, what was the first one here? I think it was 2. Then we had 5, then we had 8, let's do 11. That's a finite sequence. It's a sequence of exactly 4 numbers, 2, 5, 8, 11. So if I asked you, using this formula, to describe this sequence, what numbers are you allowed to plug in for n in this formula if it only applies to that sequence?
One to 4.
1 through 4. 1, 2, 3, and 4. Those are the only numbers that are in the domain of this formula. 5 is not in it. Why? Because 14 is not a number in the sequence. It stops at 11. It's done. Okay. So a finite sequence only uses a subset of positive integers as its domain versus all positive integers. What that highest value is, we don't know. I mean, it depends on how big your sequence is. If this sequence had 4,000 or 5,000 more terms in it, then n could be 4,000 or 5,000. But the point is, it does stop somewhere in a finite sequence. Any questions on that? Okay. So let's practice just taking a formula and listing out some terms. So list the first 3 terms and the 15th term of that sequence. Okay, what's my first term? Well, what do you plug in for n to find the first term? 1. When you plug 1 in for n, what do you get? 0. How about when you plug in 2? What do you get? 3/2. How about when you plug in 3?
8/3.
So 9 minus 1 is 8/3. And how about when you plug in, we're just going to jump right to the 15th term. What do you get with that?
224/15.
224 over 15. So maybe this sequence is approaching a number. Maybe it isn't. I mean, I know this is 0, this is 1.5. This is, what, 2 2/3. I don't know if it's getting closer and closer to a number. It might be. I think what is happening is the further you go out in the sequence, it's actually approaching the position number. Because if you take 224 and divide by 15,
Yeah, it's pretty close. It's like 14.933.
yeah. So the term in the sequence is approaching, but it will never reach its position number. That's what it's getting closer to. All right, let's try this one. What's the first term here? -2. What's the next term? 4. And the next one? -8. What would be the next one?
-16. Or 16.
16. Next one?
-32.
Next one?
64.
So it's doubling and it's alternating positive and negative. What's causing it to double is this. What's causing it to alternate positive and negative is that. So it's this is a sequence that it's not approaching anything. If you were to graph it, you know, you'd have something like -2. Let's see it. The first term is -2. The second term is +4. Then the next one is -8, and then +16. So it's bouncing up and below the axis, and it's diverging. It's approaching infinity and negative infinity. These numbers are just going to get huge. Yep.
I mean, last problem, if you do 101, it comes out to like a number that's not a fraction. It actually approaches a number.
101?
Yeah.
Well, it must be because it's rounding, because of this -1, it should always come out to a fraction.
Because 101 squared is 10,201 minus 1 is 10,200 divided by 100 is 102.
It comes out, does it come out exact?
Did you divide it by 100 instead of 100?
You said 100.
Oh, you're right.
Yeah, okay.
Wow.
Yeah, that -1 is always going to cause it to be off by 1 in the numerator. So, if you didn't have that -1, then it'd be a little different. Okay, and the 15th term, what's 2 to the 15th power?
32,768.
Yep, 32,768. And should it be a positive or a negative?
Positive. Or negative.
Yeah, the odds are always coming out negative in this formula. The even positions are coming out positive. Okay, so negative 32,768. So this type of formula is nice because you can find any term you want directly. I found the 15th term, but I didn't find the 14th through the 4th. I just skipped from 3 to 15. That's what you want to be able to do. So, if you were to graph something like this, I think I have, graph in a minute, it's going to look like a set of dots. That's what it'll look like. So let's look at an example. What were the first terms here again? Someone just remind me. The first one was how much?
0.
0, and then?
3.5.
Okay, so 1.5, yep.
8 thirds.
So 2 and a third. Okay, so if you want to graph this sequence, first position is 0. The second term is 1.5. The third term was 2 2/3. And let's just do the fourth one. The fourth one would be 15/4, which is what? 3.75? So the fourth one would be 3.75. So what's going to happen is the gap right here is going to get smaller and smaller and smaller each time. And eventually it's going to look like it's almost right on the number. Okay, like for 15 it was 14.9 or something like that. Very, very close. But that's what the graph of the sequence looks like. It's just dots. Don't connect them. Questions on that? Okay. So, we've been working with two kinds of formulas. One that allows you to find something directly, and one that you can't. When you can use a formula and calculate directly any term that you want to know, that is called an explicit formula. On the test, if I ask you for an explicit formula, and you don't write an explicit one, you write one that's the other type, which is called recursive, you won't get credit. Okay, so explicit, that's an explicit formula. That's explicit, that's explicit. That's explicit. Let's look at this one. This is recursive. That is not explicit. Recursive means it depends on the one before it to get the next one. We don't want to depend on the one before it. We want to be able to find any term directly. That's the best formula. Okay. So explicit, you can find any term directly. Recursive, what they might do is give you they always have to give you the first term in a recursive formula, because you can only work your way back so far, and then finally you get to the beginning and you just have to know that number to start. So in a recursive formula, they'll give you the first term, or maybe the first couple terms, and then the formula is defined using the previous terms. Here's a recursive formula that's a little more complicated. To get any specific term, take the term that's 2 before it, triple it, and then add the term that's 1 before it. So in this type of formula, you would have to know the first 2 terms. And then if you wanted to figure out the third term, you could. So let's say you had a 3 and a 7. To get the next term, it says, take the term that's 2 before and triple it. So if I want to know this one, take this one and triple it. I get 9. And then add the one that's directly before it, 7. So the next term is 16. And then to get the next one after that, take the one that's 2 before it, triple it, that's 21. And add the one that's directly before it, 16. 21 plus 16, 37. It would be very challenging to come up with this formula if I just gave you these 4 numbers. Even if I gave you 5 or 6 more. I don't know if most people would figure out to do something like that. That's pretty hard to figure out. And the downside is, if I want to know the 500th term, I don't want to sit here all day doing this until I get to 500. To convert this into an explicit formula, that's also pretty hard. That's not an easy thing to do. So it's not something we try to do in this class. It can be done, but not what we're going to do. Right, we already practiced a recursive sequence. Does anyone feel like we need to do another one? What does this say, just in words? To get the next term, what are you basically doing? Yep.
You add 3 to the previous term.
Yeah, that's an easy one. Add 3 to the previous one. I would expect you could figure out something like this if I gave you like 5 or 6 numbers. All right, we can try this one. Define the first 4 terms and the 8th term. Okay, what's the first term in the sequence?
2.
How do you know that? Given. Has to be given. In a recursive sequence, they have to give you the first term. So the term in position 1 is a 2. And then what are you doing to get the next term each time?
Adding 4 to the
That's it,
previous.
just adding 4. So the next term?
6,
Then?
10, 14.
Okay. So I think we did what they wanted, the first 4 terms, but there is no way to just jump to the 8th term in our head quickly with this formula. We have to keep going till we get to the 8th term. So 18, 22, 26, 30. Not too bad for 8 terms, but if I wanted to know the 900th term, you want to figure out a better way to do this. Like adding 4 899 times. So you add 4 times 899. So you want to come up with better ways than recursive formulas. So let's look at a recursive formula that's relatively simple. Not as complicated as the one I showed you where it tripled the one 2 before it and then added the 1. Just adding 5 to the 1 before it. I want to see if we can convert that to an explicit formula. What do you think we should do if we want to try to convert this to an explicit formula?
Find some numbers.
Do what?
Find it, like a couple numbers in the sequence.
Yeah, find some, write out at least the first 4 terms. You need something to look at and then see if you can find a pattern. So what's my next number?
8,
And the next one? 13. And let's do one more.
18.
18. So the idea is, can you do something to the position number to get the term number? And when I look at this, I might say, okay, I can take the position number and triple it. Perfect. Let's try it on the next one. Take the position number and triple it. Ew, that gives me 6. So tripling the position number doesn't work. A lot of times the pattern has to do with like multiply by this and then add or subtract this, if it's one of the simplest types. Does anyone see what the pattern is here? Yep.
Multiply by 5, subtract 2.
Right, times 5 minus 2. Now, how did you figure that out?
I have no idea.
Trial. So some people can just look at it and try different things in their head. There is a more systematic way to figure it out, and I'll show you that in a little bit. But for now, we'll just go with what Mabel said. So how would you write times 5 minus 2 as a formula?
Would be 5n minus 2.
Yeah, 5n minus 2. Again, n represents the position. So you want to know the 100th position? Simple, 498. Very easy now. So you should be able to convert a basic recursive into a explicit, not necessarily a really advanced recursive. Okay, so one pretty well-known sequence that is recursive is the Fibonacci sequence. And the Fibonacci sequence doesn't just depend on the term before it, it depends on the previous 2 terms. Because it depends on the previous 2 terms, I have to start you with 2 terms. Otherwise, you'd never be able to figure out the 3rd one. What does this formula basically say to do? If you want to just translate that in words, that's very simple for someone to understand. Yep.
Add the previous term to the term before the previous term.
You say it again?
Add the previous term to the term before the previous term.
Yeah, add up the previous 2 terms, and then that's the term you're looking for. So, first 2 terms in the Fibonacci sequence are 1 and 1. What would be the next term?
2.
Yep, 2, and then?
3.
Next one?
5.
Next one?
8.
I don't know how many they wanted. The first 6. We're done. 1, 1, 2, 3, 5, 8. And there is a way to figure out an explicit formula for the Fibonacci sequence. Like if I said to you, I want to know the 50th number in the Fibonacci sequence. It's going to take a little while. You've got to do it by adding the previous 2 terms. So there is another way to do it, but it's not something we get into. So that's just a very special recursive sequence. Fibonacci. Questions on that sequence? So one thing that's kind of interesting about the Fibonacci numbers is if you look at this diagram, which is Pascal's Triangle, you could easily spend months studying all the patterns in this triangle. It does lots of different things. We don't even really cover much at all of what this triangle is used for. But the idea, the way the triangle is made, is you take the previous 2 numbers and you add them together to get the one below it. So 3 plus 3 is 6, 6 plus 4 is 10, 10 plus 10 is 20, and so on. There's tons of patterns if you look at this. Actually, one pattern I remember is if you look at a prime row, all the numbers in that row are multiples of that number. So for example, 7 is a prime number. If you look at the 7th row, all the numbers in that row are multiples of 7. 5 is a prime number. If you look at row 5, all the numbers are multiples of 5. The counting starts with row 0. That's important. So what I've done here is I've drawn these diagonals. I'm going to place them right there. What I want to do is add up the numbers. Actually, I think I need to move it up 1. There you go. Add up the numbers that it goes through on the diagonal. So for example, this first diagonal, what numbers does it cut right through? 1. So add them all up. Well, there's only 1. How about the next one? What numbers does it cut right through the middle of the hexagon? Just 1. So add them up. What numbers does it cut through in the next line? Yeah, it cuts through a 1 and another 1. So we get a 2. The next one it cuts through is a 1 and a 2. That gives me 3. Then it cuts through a 1, a 3, and a 1, which adds up to what? 5. So there's the Fibonacci sequence. The numbers that it cuts through, if you add them on those diagonals, give you the Fibonacci sequence. So, and there's dozens of more things like that here. So all kinds of special stuff. That's called Pascal's Triangle. Not sure I mentioned that, but it's used for lots and lots of stuff. All right, so we classified sequences in terms of how long they are. A sequence that goes on forever is infinite. A sequence that has an end to it, what do we call that?
Recursive.
Finite.
Oh.
So explicit and recursive describes a type of formula. Infinite and finite describes how many numbers there are in the sequence. Okay. What's that?
The explicit formula, that's the one that you don't need the previous term.
Correct. Now, the pattern in the formula is usually one of two things. You're either adding a number repeatedly to get to the next one, or you're multiplying by a number repeatedly. In the Fibonacci sequence, that's a little different. Okay, so the basic ones we're going to talk about are when you add a number over and over, which is called an arithmetic sequence, or when you multiply by a number over and over. That's going to be called a geometric sequence. So in an arithmetic sequence, the idea is that there is a number you can find that you can add to the previous term each time to get the next term. So we had some like this earlier. You add a constant to the previous term to get the next term. D, or the number you're adding, is called the common difference of the sequence. Now you might think, well, wait, why is it called a difference if you're adding? Well, let's write down a sequence of numbers where we add 3 each time, starting at 1. If you add 3, what's the next term? 4, and then, and one more, 13. If you take a term and subtract the one before it, it will always come out the same if it's an arithmetic sequence. What's 13 minus 10? 3. 10 minus 7? 3. It's always going to come out to 3 in an arithmetic sequence. So D is the number that you can get by subtracting a term from the one that comes before it. If you have a sequence and you do that and it comes out different, like sometimes it comes out to 5, then maybe it comes out to 7, well then it's not arithmetic. It has to be consistent each time. And this is great. This is very easy to understand. Take the term before it and then add whatever the common difference is, but it's not very practical. Why did we say this type of formula isn't practical? John?
It takes too long.
Why?
Because you have to add all previous terms here.
Right. If you want to know the 10,000th term, you got to find every single term before it. Not that practical. So there is an explicit version of an arithmetic sequence. So this is a formula that you would want to know. So it's actually something that Nick said earlier when before we even really started, and I just said, what's the formula for this? He said something plus n minus 1 times something. Let's go back to what he said. He said something times n minus 1 plus something. That's exactly the way you start by finding an explicit formula if you don't know it. Maybe, I don't know if he already knew it, but at the time, what he was really giving me was the common difference in the sequence. That's what this is. Right here. Common difference. So that's the common difference, and that is the first term. Those are the only two things that change. D goes here, first term goes here. And then you simplify it as much as you can, right? So this formula gives you a very kind of mechanical way to find the answer. I think the way I had it written was a little different. I had n minus 1 times d plus a sub 1, just the same thing. So what he said was the same thing, just commutative property. I'm gonna do it like this. But it's n minus 1 times your common difference, and then add your first term, and simplify as much as you can. All right. So now you've got a way to figure out a formula if it's explicit. Let's try it. They didn't tell me what I would need here. You got to know the first term. Just make that up. Fine. So, can somebody tell me what's the explicit formula? Don't fill anything in. Just give me the general version without any numbers. Yep.
A1 plus n minus 1d.
There you go. Okay. What's going to go in for a sub 1? 5. That's a given. They have to give it to you. I didn't have it written down, but I had to. You need to know it. Plus n minus 1. And what's the common difference?
3.
It's what you're adding each time. When you simplify that, what do you get for a final answer? 3n minus what?
Minus 4.
Minus 2.
I mean plus 4.
Plus 1.
Minus 2.
What's negative 1 times 3?
Oh.
Negative 3 plus
So
minus 2.
2.
Isn't it positive 2 though?
Yeah, it would be positive.
Yeah, positive. So, triple and add 2. That's the formula for the sequence. I'm not going to go through and try it, but you could try it. It would work. That's your formula. Let's see. So this says the first two terms in an arithmetic sequence are -8, -2. Find the fifth term, and it looks like they want a formula. Okay. So the first two terms are given. So this is term 1, this is term 2. So what's a sub 1?
-8.
And what's the common difference here?
6.
6. It's what you're adding each time to get to the next term. So let's write down what the formula would be. What would I put here for my explicit formula?
-8 plus n minus 1. 6.
Plus n minus 1 times 6. And that will simplify to
3n minus 7.
6.
6n.
No.
Negative 14.
Negative 14. Now, we only had to find the fifth term. We probably could have done that faster without even doing this. But if they wanted the 507th term, then you definitely want to find the formula and now fill in 507. We're only filling in 5. So what's 6 times 5?
30.
And 30 minus 14?
16.
60. So a sub 5 is 60. Questions on that? So that's doing it explicitly versus just saying, okay, I'm going to add 6, and then add 6, and then add 6 again. Okay, find a formula for the arithmetic sequence. All right, they give you the third and the eighth term. If all they said in writing was the third term is 13 and the eighth term is 3, you're probably going to want to make a diagram like this. How are we going to figure out the first term? We need to know it. Yep.
Would you find the difference between 13 and 3 and then even 5 between to find how much you're adding.
Yeah, you gotta figure out what the steps here are. They don't have to be the same because it's arithmetic. So what are you doing each time to get from 13 to 3?
Adding 2. Or
Yeah.
subtracting 2.
You're subtracting 2. So this would be, let's try it, 11, 9, 7, 5. Now work your way backwards. What's the second term?
15.
And the first term?
17.
There you go. Now you know the first term is 17. You know your common difference is how much?
Negative 2.
-2. 13 minus 15 is -2. Plug those into your formula and then you got it. Any question on how you find the formula? Okay, and I think that table kind of helps to visually see this problem. So the other type of sequence, and the last one we're going to look at, is a geometric progression. So we have arithmetic and geometric. These two words describe how you're getting from one term to the next. Are you adding? Or are you multiplying? So in this type of sequence, you multiply the previous term by a constant. So recursively, this is what it would look like. To find a particular term, take the one before it and multiply by r. R is called the common ratio. So let me write out some terms in a geometric sequence, and you can see why it's called a ratio. Let's take this sequence. If this sequence is geometric, then you should be able to take a term, divide by the one before it, and always get the same answer. What's 48 divided by 24? 2. 24 divided by 12?
2.
And 12 divided by 6? 2. If you take a term and divide by the one before it, you will always get 2. That means it's geometric. And r, in that particular case, is 2. Take a term and divide by the one before it. Now, if you try this on the last problem, it won't work. You'll get a different answer every time because the last problem was not geometric.
Why is it an plus 1 step minus 1?
Because it's the term, I mean, you could write it, so you have to basically write like this. A term divided by the term before. You can write that lots of different ways. If you want to write this as the term, that's fine. What's the one before that one?
Oh, an minus 1. Okay.
So you can write it that way too. That would mean the same thing. The concept is take a term and divide by the one before it. Okay, and in general, it's kind of tough to figure out a pattern here. I mean, I know it's got something to do with a 3, because that's the first term, and that's what I'm multiplying by each time. So, oh, you have to kind of think about what can you do to this number to turn it into the one above it. Well, let's try that. If you plug in the first term, 1 minus 1 is 0. What's 3 to the 0? 1. What's 1 times 3? 3. Okay, it worked. Let's try it again. Second term. What's 2 minus 1?
1.
1. 3 to the first power?
3.
3 times 3?
9.
9. Okay, so didn't quite work there. So it's harder to figure out what the pattern might be.
Yeah, one of those spiffy formulas we can plug into.
You do. You have a formula.
Awesome.
which I thought I was using in the last one. A sub 1 r to the n minus 1. So 3, 6, 12, 24. Oh, we're not multiplying by 3 each time. We're multiplying by 2. Huh? Okay. So 3 times 2 to the n minus 1. 1 minus 1 is 0. 2 to the 0 is 1. 1 times 3 is 3. Try the second one. 2 minus 1 is 1. What's 2 to the first power? 2 times 3? There's your second term, 6. Let's try the fourth one. 4 minus 1 is 3. What's 2 to the third?
8.
And what's 8 times 3?
24.
There you go. 20. Well, so here's an explicit formula for a geometric sequence. Let's try one of those. Find an explicit formula for the geometric sequence.
Oh, that's wacky.
So they didn't quite give you what you needed. What's the first term here?
Three.
3. And what are you doing each time?
By timesing by -2.
Timesing by -2. So here's your formula. A sub n equals the first term times r to the n minus 1, and fill in what r is. -2. Let's try it on the third one. What's 3 minus 1?
2.
2 squared?
4.
4 times 3? Perfect. So there's a formula that will give you any term in the sequence you want to know. All right. So that covers pretty much everything that's on the test. So tomorrow, if you are going to be absent, you can take the test. We have the math field trip on Friday. Otherwise, you could also use tomorrow as a review day. You can work on your reference sheet, ask me questions. And then Friday will be the day that everyone else can take the test if you're going to be here. All right, so this is, let's just simplify that, 1 through 13.
What are your opinions, Mr. Hager, on how close it is to the end of the year?
How close? Well, when it seems like it went by quick.
Yeah.
Yeah, another one done, almost. Getting there.